Schmidt on Efimov physics beyond universality. So please.
Thank you, and also thank you for having me here for this talk. I hope actually I just told Seth before, because I still have my cold. I hope that if anybody is watching actually the video, one should probably put a disclaimer that one destroys the ears probably if I have to cough in between. Well, let's start with the talk. I will talk about recent work I did together with Willi Zwerger and Steffen Patrick Rath at the University in Munich. And we looked into a problem, I think Chris Green spoke about it also last week, the universality of the three-body parameter, or this apparent universality observed with ultracold atoms. So let me say a few words about these ultracold quantum gases. What one is doing there is one traps ultracold atoms using laser light and cools them down to very low temperatures, and then presumably at these very low temperatures you can describe the collisions really well by the use of contact interactions, because every interactions but the S-wave interactions are frozen out and you have really short-range interactions. Now what is very nice about these systems, you can tune many knobs in these systems. For example, the interaction strength between these atoms, and what you arrive then is at a system, a condensed matter systems, where we have an action, or it's described by an action or Hamiltonian. We are really certain that it's really describing the system we are looking at in the experiment. And this is different from typical hard condensed matter systems, where you might argue a lot which Hamiltonian is actually describing which high-TC superconductor, for example. Now, by having such a simple Hamiltonian, for example, here bosons interacting with the contact interactions, and I'm speaking about these non-relativistic guys, one has really a system which is ideal for testing many-body theories, because one can really go to, for example, the strong coupling regime and then test many-body theories versus really the experimental results. And this is what was put forward by Feynman. It's the idea of a quantum simulator. And let me give you two examples. For example, the strongly interacting two-component Fermi gas, the so-called unitary Fermi gas at infinite scattering length, where you can measure then, for example, the equation of state, pressure versus chemical potential. And the most recent data and most accurate data so far was obtained by the MIT group, by Martin Swearlein. Here the red data points. And this can be compared to a huge mass of many-body theories. It's a strong coupling problem, so very hard to calculate. And I would say by now the calculations using diagrammatic Monte Carlo or DFT calculations, which are also done here, are in excellent agreement by now with the experimental data. A much more simple problem is, for example, if you insert a single impurity in a Fermi gas, the so-called Polaron problem, and then you can predict also in the strong coupling regime, so here's interaction strength versus frequency of an RF pulse. You can predict the RF spectrum and compare this then, for example, to the experiment. And this is done with a calculation and method I will also use here, the functional renormalization group. And this is one example of this testing many-body theories.
Okay, maybe this is a premature question, but to know the scope of your talk, are you going to be talking about fermions?
I will talk about
fermions?
bosons.
Then I'm not sure why you are confident that that action is sufficient. For example, what about the three-body force?
Yeah, we will come to all these questions. No, this is more like introductory slide coming from the many-body direction. This is if you look in the review like Ploch, Dalibard, Zwerger, then this is the basis of everything. You start with this action, sometimes you put them in the lattice, but it's basically that for many-body calculations, very often just a contact interaction is used. I will come to the details. They will become important in the remainder of the talk.
I think that's a detail, but okay, all right. I'll shrug.
Well, yeah. We will come to the conclusion that's a detail. That's in fact true. But let's go on and let's see where the detail comes about. Well, so we have this model Hamiltonian. It's really simple, really nice for calculations. However, one should be aware that the better the experiments become, the more careful we have to be that actually the experiments become so sensitive to be actually sensitive to non-universal corrections or to corrections to this Hamiltonian-like effective range and so on. So many-body calculations can become more complicated to fit experiment, the better the experiments will become. Now also one should probably not reduce cold atoms only to this concept of quantum simulation. It's probably not really fair to do so, because it's really also a unique system to study this interplay between few and many body physics. This is very hard in the typical condensed matter system with electrons, for example. Also, there are then effects in these systems which don't have a direct counterpart in hard condensed matter systems. And in this respect, for this the topic of this talk, Efimov physics really combines these things. Like you have to care about these corrections to the Hamiltonian. You have this interplay, few many body physics you have to think about. And it's an effect which has no direct counterpart in hard condensed matter systems like in the solid. Now, before I come to the three-body problem, a short comment on the two-body sector. If you have two particles interacting with at low energies via S-wave scattering length, we all know that. If I plot the inverse scattering length, we have no bound state for negative scattering length and the famous universal dimer for positive scattering length. And it does not matter as long the interactions are short range. The details of the interactions, it's always this law 1 over a squared. Now this is one important concept, this of universality, that no matter the microphysics, you get always the same macroscopic answer in the experiment. And so your physics is really dependent only on a few numbers. Here only the scattering length.
But you're not implying that the interaction has to be local, or are you?
No, it does not have to be. It has to be.
Right v of x prime minus x?
No, it does not have to be of this form. So you can have x comma x prime comma x prime prime. You know, if I do it with all, okay. So please ask me if there are details. Sometimes I'm a bit sloppy in the notation then.
Just to sort of make sure we know what you're talking about, are you restricting yourselves to broad resonances? Or
I will come to this in a second.
Because I mean, this two-body.
This thing is a single channel
Okay, so you're
potential, but we will come to a two-channel model later on. This is more like to have the flavor what actually Eflmov physics is doing with us. So if I take now the scattering length to infinity, then I'm actually also lose this only scale the scattering length really in the problem, and I reach scale invariance. And this is a very powerful symmetry, which, for example, also there are many papers exploiting this even to calculate the exact time-dependent problems in the many body.
Because you have to fix the short-range behavior. So you have two scales in Efimov physics. You have the short.
No, that's why I say I talk about two-body on the slide. Give me 2 clicks, and I.
Three-body spectrum. No.
Two green guys. On the next slide, I will have 3 green guys.
We shouldn't have given an introduction.
Why not giving an intro?
No, I agree with you. Your slides are very fine. So,
Okay, so both of this is connected actually to the existence of an RG fixed point in the two-body sector. And now what we all know is that Efimov predicted for 3 particles that if they interact with resonant short-range interactions, we have this famous Efimov spectrum with infinitely many bound states. And here's the unitarity point where actually the states behave in a universal way, that you have here constant ratios between these energy levels, or here between the scattering length where they reach the atom threshold. I think everybody here is familiar with that. But what does it do with the concepts I just introduced? The problem is scale invariance is gone, which is a problem for many body calculations if you want to rely on the symmetry, and you're only left with scale invariance, discrete scale invariance. You introduce now a ruler in your system you can measure energies with, just these green states. Now the second is the RG fixed point, as we will see, will be supplemented in the 3-body sector by RG limit cycle, which is just a reincarnation of this discrete scale invariance. And now to your question. Also this concept of universality only having one parameter is gone, because we have to actually introduce a 3-body parameter. And this is because Efimov tells us that there are these infinitely many bound states, but he does not tell us actually where in the spectrum they lie. And I have to fix, for example, where one of these trimers hits the atom threshold and this one calls the scattering length A minus. So this is one way to parameterize this three-body parameter. Now the origin of this three-body parameter, if you come more from a quantum mechanics perspective, where one calculates, for example, this problem in the hyperspherical formalism, one has the three-body potential with the 1 over r squared law, which is cut off here by the scattering length. But here at short distances, if you don't regularize it, you would have infinitely deeply bound states, which is the so-called Thomas collapse. Now you regularize the problem, for example, introducing here a repulsive core, and by that you actually fix the energy of the lowest trimer states, and with that also the scattering length where actually this trimer state will hit the atom threshold. If you come from a field theoretical perspective, you can, for example, calculate the RG flow, like nicely done for the first time actually by Bidak and Hammer and Van Kolk, and I forgot one name. Well, and what you have there is that you look at the evolution, the RG evolution of the three-body coupling constant. If it has divergences, it means I have a bound state in the spectrum, and now I fix actually the position of these bound states by fixing the position of these divergences in the RG flow. So if I put this high energy scales right or left here, I fix actually A minus again. But in both cases, these parameters are short distance properties. And being short distance properties, one would guess, well, this number should be non-universal. And this is also nicely discussed in this paper over here. Now the question is, how do we observe Efimov physics with ultra-cold atoms? So I'm sorry if I'm bothering you with this introduction. I thought maybe if people are from the nuclear community, I just do that one more time. How do I measure actually this A minus parameter? And what you do is actually you exploit three-body loss in these cold atomic systems. What you do is you collect your bosons in an optical dipole trap. And what can happen if we look here at the energy spectrum, so here I have my typical three-body spectrum, trimer states, my dimer. And what can happen is I have three atoms, they come close by, two of them can actually build a deeply bound molecule. These deeply bound molecules are, for example, the low vibrational state of the two-body interaction potential, and they can decay into this. However, if I have two particles, they collide and would like to recombine, a third particle has to come and take away actually the binding energy, and this is then transferred into kinetic energy. So what happens in my trap? I have a recombination of two of these guys, and then these guys have kinetic energy, and it's so high that they actually leave the trap. If I take now a picture of my atoms after a while, I will see that I lost atoms, and what I can plot then is the inverse scattering length versus the loss rate in my system, and the loss coefficient can be shown goes via this, due to this process, like scattering length to the fourth power. Now what was shown in the seminal paper back then is if we have now in the spectrum also a trimer bound state, what happens is that my three atoms can come together and they can build a virtual trimer bound state, which then subsequently decays into these deeply bound dimers. So what I do is, like in typical scattering experiments, I open up a new decay channel, and therefore I will get at this position a lot in enhanced loss. And now this coefficient, for this reason I have a coefficient in front of this a to the 4 law, and this was calculated analytically, and it's much used since then by these guys here. Now this was exploited then, in fact, in 2006 in the first observation of Efimov physics, where bosons were used by the group of Rudi Grimm in Innsbruck, and they just saw one of these loss enhancements, and this just tells you where A minus is, or what is the quantity A minus. Also, this was done, for example, with 3-component fermions. Also those have the Efimov effect, and then here are the experimental points again in the theory curve, here in FRG calculation. We did back then, and at the same time also from EFT calculations by Hammer and Braten and Nidon and Eder. So finally, let me come to what happened till 2012. Many experiments had been performed using many different kinds of atom species, and what happened, one would assume that this A- parameter should, if it's non-universal, these numbers should be kind of random. And let's say if I look how big A- is with respect to the van der Waals length, I should expect all kinds of values. However, what happened is that all values really scattered in the 10% window around 9.2 van der Waals length, which was a surprising effect. And
Potassium,
again?
but not potassium.
Oh, this one has, so I took the data here from Chin's paper. This has to be crossed out. In this one, they actually mistook a 4-body resonance apparently with a 3-body resonance. So, but I just kept it because otherwise I would delete something from the citation of the paper.
This problem is fixed now.
This problem is fixed. So this value is gone. I will come to this in a second.
This universality, why do you quote that to the first number after the decimal point?
Again?
Why is this 9.2? I would say it's rather more like 9.
Absolutely.
Look at those numbers.
I would therefore should have put this as the quotation mark is the important thing. No, it's not universal in the thing that it has to be 0.2.
So 9.2 is just the average of
This is the average, just the average taken, which they did in this paper.
The other numbers, except for potassium, they more or less stand, or?
They more or less stand, I would say. They are actually by now even more numbers. And they all are within this, I would say, 15% region. Or, but it's around, it is around that value. So this is really the average, which they did in this, what I think Chris Green sometimes calls the bombshell paper. Well, okay. Now, where can this come from that actually, although I use really different atoms, I could get almost the same result all the time. And when we looked at that, we thought, well, if you want to test universality, you have to change your microscopic physics. And the question is if all experiments and all of those exploit Feshbach resonances. So in the end, one could think, man, in the end, I'm probably not really testing universality because I always use Feshbach resonances. It's always the same mechanism. So it's not so surprising from that perspective that you maybe get similar numbers out of these experiments. So this was our starting point. And then our goal was, let's test this kind of universality by using a simple Feshbach resonance model without any fit parameter. So we want to have a model where we take the results from two-body physics measurable by the experimentalists and have no fit parameter and predict which three-body parameter comes out, which A-. And let's see if this works. And we wanted to do this with a renormalization group, having in mind that in the end we want to have a model which, for example, can be used for many body calculations. For example, if you want to do something with a unitary Bose gas, you have to have a model which does this correctly, and then you can go on. So that's the reason why we did not do, for example, some more complicated models, including really realistic single-channel potentials, like what was done by Jia Wang and Co. and Chris Klein and Rosé. Before I come now to our results, let me introduce shortly this functional renormalization group approach. It's based on quantum field theory, and what you do is you look at your system as a theorist. Here, for example, a Bose gas, you write down your action, and this is defined at some UV scale. Here I have bosons interacting again with contact interactions as an example with a non-relativistic propagator. Now if I want to make connection to experiment, in the experiment they measure correlation functions. So I have to have a theoretical tool to get access to these correlation functions, and for instance I can calculate the partition function. Equally well, I can also calculate what is called the effective action, which is the generating function of so-called one-particle irreducible Green's functions, but it's really equivalent to this partition function. What it does is it's a very physical object. It actually describes the propagation of my full quantum particle degrees of freedom, which means that these are bosons here, which propagate through the system, including their self-energy, which might, for example, account for the effective mass, and it will give you the full spectral function. Also, this object has then a scattering term between these quantum particles, degrees of freedom, which include all quantum and statistical fluctuations, which gives you access, for example, to the correlation function corresponding to the scattering amplitude. And here, of course, you have only experimentally accessible parameters which are measured, like the scattering length. And you can get much more out of it, RF responses, Fermi liquid parameters. Actually, it includes everything if you could calculate it. Now, the problem in calculation of this effective action is, and we talked about that yesterday shortly in the discussion also, that you have a build-up. Let's assume I start with an action with only two particle scattering. Of course, I can build up 3 particle correlations. This is also important for our Efimov effect. So effectively, I have a scattering of 3 particles, and if this scattering amplitude has a pole, well, this is like a 2-particle scattering, then I have a bound state. This will be the Efimov states. And this is related, in fact, then to the hyperspherical wave function just now in momentum space. So this is the connection. So in fact, this contains the full density matrix. Of course, then we have to have all these wave functions inside, and these wave functions are here.
If you're going to look only at the loss rate, you're going to solve the 3-body problem. What's wrong with Faddeev equations?
Oh, it's absolutely nothing wrong with that.
Why are you using a different tool?
This is what I said before. If we want to go on to the many-body problem, so what I showed before is, for example, this polaron problem. There we use the same method, the same model. And
are you going to go on, or you're going to do only the 3-body?
Here I only do the 3-body problem.
So then everything you obtain is the same thing as
Absolutely. But I mean, if the world would be like this, that everybody is doing FRG, everybody would ask, why do you use quantum, why do you use Faddeev equation if you're more comfortable with using this? It's a matter of taste. But since we used this,
it more than 10 years now, right?
Again?
We know the loss rate for about 10 years or so, right?
Yeah,
Problems.
absolutely.
So now what will be new in your talk?
New will be that we start from a model, a simple model, where we take the input from experiment and try to predict the 3-body parameter just by this input. It's very similar to what was done, for example, by Rosé in his paper.
But your simple model is not what
Oh, no. We are not yet.
Something different what you take.
Yes.
Why not to take van der Waals interaction directly, you see, and not take a model, because there's the real interaction. That would be more interesting.
And if we do it with the van der Waals interaction, we also have to account for the 2-channel character of resonance.
Put a cutoff, you see, at some certain radius, and use a pseudo potential, and then it'll be fine.
To use a what?
You can use a pseudo potential, you see, like typically people use in order to cut off the short range part.
But with this, it will turn out that then you have to fix, for example, the phase of your scattering problem, and then you're back that you have to put in this 3-body parameter by hand if you use pseudo potentials. This is what is done typically in EFT approaches, or what we did back then, for example, for the fermions.
The problem is also very artificial. So
sure.
I don't see why.
I mean, in some sense, the Fermi-Hubbard model is also artificial.
I don't know why one is better than the other approaches.
No, I don't say that it's better.
One simple model that can predict the 3-body parameter, and then he takes his pick.
Exactly. And the point is, I want to use the method I know, so I use this method. But if people don't know the method, I decide to say at least shortly what the method is about. So that's, I mean, it's very similar. I mean, if you do a DFT calculation, it's also this object which you take and try to improve and improve. So
What we can do is just go through and see what your approach can yield, and then after the talk we can sort of compare the merits of
yes, absolutely. So the question is how to obtain this object, and what one does is one introduces an interpolating effective action, which has a similar form than the full result. However, what one does is one introduces these so-called coupling, or these are coupling constant or self-energy, which is dependent on some scale k. And this includes only fluctuations and statistical fluctuations on momentum scales larger then this momentum k, or this RG scale k. And what one has then is, if k is just at the scale where you define your action, this self-energy is just gone, and you start actually with your normal classical action. And if k is equal to 0, you should end up with your full effective action, where you have access then to all correlation functions. Now, what is good about the formalism, that you in fact have an exact RG equation which tells you how this object gamma k transforms from the classical action into the full quantum action. So in principle, you only have to plug it in and solve it, although it's a hard problem. But this we do now actually for this three-body problem. Let me give you a short illustration how this in principle looks like. You define your action with some coupling constant, for example, the contact interaction term, and simple many-body approaches to cold atoms. Then you integrate out fluctuations on small distance scales, large momentum scales, and at these scales, particles are at most, in some sense, sensitive to really their close distance surroundings. And so the initial steps of an RG flow, my coupling constant will change, but this change is determined really by few-body physics. You go on, maybe three-body correlations are important. You go on, and then at some point you reach really the realm of many-body physics. You see that there's density in the system, and you encounter, for example, quantum criticality, stuff like this, phase transitions. And in the end, you hope that you solved your problem. Now let's think, if you would like to solve the two-component fermion problem, one would start with a little integrating out fluctuations, and maybe one encounters the kind of the two-body problem. This one has to know. One has to be sure to know how two-body correlations work. If I go on, there might be now a third particle, and well, this has the same spin than one of these guys, so one might argue, maybe because of Pauli blocking, these correlations will be suppressed. In some sense, this is a little bit why BCS theory does even work somewhat for even the unitary Fermi gas. BCS theory only takes into account these two-body correlations. Now, if you do identical bosons, you have to be much more careful in the many-body problem. As you go from 2 to 3 particles, for example, there's no reason, or there's no Pauli principle protecting us from the buildup of strong three-body correlations. And what we see there is then that we really have to have this deep understanding of few-body physics before we can do a reliable many-body calculation. So this is kind of the reason why I did this I want really to connect when few and many come together to produce problems. And especially right now, the unitary boson gas gets studied a lot, and these are things one has to think about. Now, the flow in the three-body problem of coupling constant looks now the following. I don't have a three-body term in here, for example. I will have a three-body term later. And I have a buildup of three-body correlations. If I have fermions, the following happens. I have 0 coupling in the beginning, and then I have a buildup of a little bit a three-body coupling constant, but it's flowing to a so-called fixed point. This means as I change my RG scale, the coupling constant does not change, and it means I have a scale invariant system. So here I see fermions don't kill my scale invariance, which I had in the two-body problem.
What would be the physical picture of this lambda 3 in the two-component Fermi gas if I have 2 up and 1 down particle?
You could, for example, view it like, it might be, if you start from a two-channel model, for instance, it might be the exchange should have 2 fermions up and down coming together, building a virtual molecule, and then this virtual molecules via atom dimer scattering scatters off a third guy, and you would find here something like this famous result that in the infrared you have this 1.18 by Petrov 2004. Yeah, so this is the meaning of, so this I call lambda 3.
Okay,
It would have to be a
related question.
derivative.
Oh.
Sorry, it would have to be a derivative interaction, though, right?
Again?
It wouldn't be a local, are you saying that the
Yes.
pi-
This is still schematically.
But a related question. I mean, there's a scale in this lambda 3. There's also a scale in your GK. So Is this a calculation, or you're just arguing in terms of dimension analysis?
Oh no, this is a sketch, but these calculations had been done by Hans Wermer, by us in the long paper 4 years ago for two-component fermions SU2, SU3.
Okay, so I haven't read this paper, but I mean the scale then given that appears in lambda 3, the mass scale, say, or distance scale that appears there, that's consistent with dimensional analysis?
This is consistent with, of course.
Okay.
So for bosons, what you encounter is not such a nice fixed point, but this famous limit cycle. And here you see this is not scale invariant as I change my RG scale k, so my scale invariance is broken, which is bad for many-body calculations. And again, we have the 3-body parameter as a short-range quantity. Now let's come back to the question, why did all the experiment find this 9.2? And now let me finally introduce the model which we have. And what we take is we want to describe these atoms close to a Feshbach resonance. And what we take is a very simple model, 2-channel model for the scattering, but it's still so simple that one could trace a many-body calculation with it. For example, we used it to look at this Polaron problem of atoms close to a narrow Feshbach resonance, where it worked quite nicely. So what you have is atoms in an open channel which propagate normally with a non-relativistic dispersion relation, and they interact with each other via the exchange of a closed channel molecule. So what can happen is, or this molecule is described here by the field phi, and it has an energy which is detuned via a magnetic field from the atom threshold. Now these two atoms, they become a molecule via a conversion term. Here 2 atoms are destroyed and this molecule is generated, and this gives you then this effective scattering of the particles. Now in the EFT approaches, like in the beginning, or also what we used for the SU3 fermions, one takes a zero-range model for this conversion coupling, and where this is then replaced just by the delta function. So the atoms really have to be on top of each other to go into this molecular state. But now if you look at this picture, in cold atoms we mostly have actually low magnetic field detunings, where the relevant molecule in the closed channel is rather weakly bound. So the wave function will be rather far extended in space. So one might argue that it makes sense that this conversion coupling actually does not only exist when the distance is 0 between the particles, but they can already form this molecule when they are quite far away. And therefore we introduce a coupling constant which has a finite range and some coupling strength G. Now what we want to have is we have our model which has 3 parameters as input. It's this detuning, the range of the conversion coupling, and its strength. And we want to get everything out of the experimental data. So the experimentalists should tell us what they have, and we predict then the 3-body physics. So what we do is we solve the 2-body problem analytically and extract the magnetic field dependence of the scattering length, which is given by this molecular exchange, and get some profile for the scattering length. This one can then compare to the phenomenological formula which experimentalists often use to characterize Feshbach resonances, where you have this width of the Feshbach resonances R star. Now, by comparing our A of B with the phenomenological formula close to the resonance, we fix our strength by this R star parameter. This is accessible in the experiment. Second, it turns out that we can then get this B res value by the actual position of the Feshbach resonance, again out of this formula of A of B. Also this can be obtained easily experimentally. And third, we need the range of our interactions, and what we do there is a shift between the position where the bare molecular state crosses the threshold and where the actually resonance appears, B naught. So what we do is we calculate the so-called resonance shift in our model and then compare to a 2-channel calculation with van der Waals tails, which was done by Paul Julien and Goral and co-workers, and they actually derived a analytical formula for this resonance shift by comparing our formula with theirs, or these two results. We find that sigma is 0.95 the van der Waals length. And with this, everything is fixed really from experimental input data, van der Waals length, resonance position, and with all the Feshbach resonances. Now we are left with what we have, no fit parameter at all, and we have to live with the outcome. If it's bad, it's bad. If it's good, it's good. But okay, one has then to go on and test universality, which we did as well.
Is there a specific reason you choose this Yukawa form for the finite range?
No, we chose different ones. So to test universality, you have to change microphysics. Well, you could argue a bit this Yukawa term, it mimics a bit the wave function form of a weakly bound dimer state. So if this would be a very weakly bound state, one could argue that the wave function exponentially decays and they are therefore such a form. Makes sense. There is a second thing which is nice about this form factor. If you calculate the effective range in this model, we find that it's given by 3 times the van der Waals length, and there's this Kriba-Kim-Flambaum calculation using really van der Waals.
Where is the van der Waals length there?
Where? Here?
Yeah.
Here it comes from talking to Paul Julian and using their resonance shift in a 2-channel model, including Feshbach resonance.
In this
van der Waals.
model, it's 3 times sigma then.
In this model, what? Yeah, absolutely, absolutely. However, if you take a Gaussian, you get a different. But it's an indication that this might be even senseful. Sorry.
Before you go to the 3-body part, have you tested this model, this 2-body model, for example, by comparing the binding energies you get, right, for a given R star and the sigma?
Yes.
I mean, if you are talking to Paul Julian, he has those bound.
Yes, I know exactly what you mean. So I did that actually a lot. So there's this new Florence experiment. And I stayed with them for 3 weeks, and we did that the whole time, because they also do it in the experiments. And these models, for example, if you compare the dimer binding energy calculated with these models, change, for example, this form factor. I have to say this is good, close to resonances, but the dimer binding energies in these models never fits very well what you measure in the experiment. Is this what you mean?
Sure, yeah. No, like, if you go to, a very narrow resonance, our star is very large.
Absolutely.
So I think this should be very sensitive to that parameter, for instance, even if the scaffold is large.
Yeah, one has to be a bit cautious. If we talk here about the effective range, we know where in our calculation use the effective range.
Sure, yeah.
This would give horribly wrong results for broad Feshbach resonances, for instance, because it does not reproduce at all. You can even have divergences in your 2-body energy.
And really, your model does not have an effective range. Like
No, it has an effective range, but only because
you introduce by hand.
No, of course the model has an effective range. If I take my scattering amplitude, which I calculate from this process, I expand it in K, of course I can do an effective range expansion. I can read up the coefficient.
But is that?
But I never start and say, well, let's use a simple model where I only use minus a to the minus 1 plus 1/2 r effective range k squared minus ik. This would give bad results. Of course, you see it, the bound state spectrum is really poor of such a model.
Yeah, it's clear. You have the other effective range parameters, the shape parameter, and so on.
Yeah, I mean, if we expand our thing, we have infinitely many k to the power in infinite terms. Yeah, sure.
Now, in Julian's calculations, the size of the closed channel molecule and the van der Waals lengths, how do they compare?
If they consider a weakly detuned closed channel molecule, they compare they are of the same size. Or actually the bound-state molecule is a bit larger. If you are aiming how big the range of the conversion coupling is this what you aim at? No.
No, I'm simply.
Okay, no, they are
What's
of the
size?
same order or actually larger for weakly bound molecules in the closed channel. If they have, of course, a very deep vibrational level, then it's smaller than the van der Waals length. But this would correspond to a few thousand Gauss in the experiments which they don't use. I hope this answers. Well, just for one thing, one very often uses the so-called strength of the Feshbach resonances, which is just the inverse of this range parameter. So if I have a large strength of the Feshbach resonance, I have a very so-called broad Feshbach resonance, or if it's very small, then I speak of a closed channel dominated resonance. One should actually be careful with the use of narrow and broad Feshbach resonances. This is actually reserved for the many-body problem by comparing these values with the density. So one should better speak of closed channel dominated resonances if I have small S-rays, and open channel dominated if I have these largely extended Feshbach resonances. Where does this come from, this notion? If you calculate the scattering length depends on the magnetic field, you have this exchange of this molecule, and this has a propagator, the Baer propagator, and then the quantum correction, which is of course proportional to a G squared, my Yukawa coupling squared. Now of course if G is very small, then everything is dominated by the closed channel, by so to say classical physics, and if I have a large G, everything is very much quantum, and one calls it in opposition than the open channel dominated case. So finally, we solve the three-body problem exactly using this RG method. So we write down our ansatz for the effective action, which includes, for example, the atoms propagating the system, the dimers, which have now this full self-energy term. We have this conversion coupling of two atoms into a molecule. And then what is generated is the scattering of the atoms with the dimers, which I drew down here. Here's one dimer and an atom, and they scatter off each other, although here it's for bosons, of course. Now, this is a complicated function of momenta, and this in this problem you have to solve by inserting this effective action to our flow equation, and then you solve the two-body problem by calculating these diagrams, and then the three-body problem, which consists then of solving this atom-dimer scattering problem. And now back to your question. Of course, in the infrared, we solve this analytically, what we of course get back is the Lippmann-Schwinger equation and the modified STM equation. It has to be because it's exact and STM is exact as well. Now to show, instead of going in more detail in the calculation, how does such a flow look like? If I look at this three-body correlation or coupling term, it's dependent on two momenta. And if I plot it now, as I include more and more quantum fluctuations, here I show the typical flow in the gradient expansion, which is more familiar to people from when one reads, for example, reviews or older papers. This is very similar to what I also did with Sergei Morris a few years back. Now, in the classical action, I have no three-body correlations, no three-body force, so there's just zero of this coupling. Now, as I integrate in more quantum fluctuations, I have a build-up of fluctuations which becomes stronger and stronger, so it's also shown here, and at some point it becomes so strong that I actually encounter my first divergency, which means I have the first bound state in my spectrum. And what happens then, a periodic structure appears in this full momentum space, and what I actually did not say, the flow actually only starts at about 2 times the range of this interaction, so by about 2 times the van der Waals length, so correlations are suppressed on scales below that. It's somewhat similar, I think. If you would take the Fourier transform, it would be interesting to see actually how it compares to the hyperradial wave function. And then you go on and you calculate your flow, which in the end is suppressed by the scattering length. Of course, in the typical quantum mechanical approach, where you have the hyperspherical potential, this guy has 1 over r squared, but it's cut off to an exponential at the scattering length. It's the same what we see here, exponential drop off of our calculation when I hit the scattering length.
In your 2D plot, what you plot here is finite, but it's really also divergent at this.
Yeah, you know what? You know here sometimes the scale it's jumping from 1, then sometimes 2, then it's yeah. So there are really divergences in between. It's only it looks very bad if you show it with a constant scale. So in the end, what we get is then our full infrared coupling, and then one can go to actually beautiful pages in this review by Hammer and Braten, who tell everything how you extract bound state spectrum, decay rates, everything. So we use actually our object here and calculate the bound state spectrum. Here showed for an open channel dominated resonance, inverse scattering length versus energy, typical Efimov spectrum. As I go to smaller Feshbach resonances, more closed channel dominated, what I find is that these trimer bound states get pushed towards this unitarity point, and they get pushed and pushed more into this direction. However, if I go to broad Feshbach resonance, open channel dominated ones, what I find is that they can only reach a finite extent, and then they cannot grow anymore in energy scattering length plane. Back to the question, I forgot who. Yeah, Frank Kolk actually asked it about the problem with this. No, it was actually you. With this dimer binding energy. One has to be very careful. I would not trust our results at the dimer binding energy for one reason, because the dimer binding energy itself is highly non-universal as you go away from the scattering threshold in this model. For example, you see here, for open channel dominated resonance, it looks like that. Here, it looks different. So one has to be careful with this. This does not apply to this regime here. However, we get this maximal extent, and then...
Richard, in your previous graph, can you say what you mean by this pushing up toward unitarity?
Yes, if I would go... Sorry.
Is it just the lowest state that gets pushed?
No,
or is
everything,
the
of course.
spacing being changed?
It's all. So, of course, if you are here, let's say you go to the 4th or 5th state, they have the universal scaling. The whole spectrum itself, however, the whole spectrum gets pushed in this direction, keeping these distances approximately. Maybe on the next slide it becomes more clear.
But when you say the whole spectrum is pushed up, doesn't that just mean it's a different three-body parameter?
Absolutely.
So if you look close to zero energy, then it's universal for open channel and it's universal for closed channel.
That was my question.
No, but what do you mean? No, so what? Of course, it's completely universal here, but this thing here, where this comes in, is just the three-body parameter. This defines the three-body parameter.
Let me state this differently.
Yeah.
If you look at the deep states, it's neither universal on the right side nor it's universal on the left side. If I look at the plot.
No. The point is, if I have open channel dominated resonance, if I introduce, for example, as we will see in the second, three body forces, different form factors, this figure will look the same. If I keep S, the strength, the same, if I stay in the broad Feshbach resonant limit, then the picture will always stay the same. What I find is there's one additional parameter. This is the strength of the Feshbach resonance. Choose one strength of the Feshbach resonance, you get a universal plot. Or universal with deviations on the order of 10%.
All right, so then it's the question, what do you define as universal?
Absolutely. Therefore, we call it also beyond universality, because it's not really universal.
Yeah, so the way the deep state here behaves, maybe it's universal in your sense, but not in Efimov's original sense, right? Since it looks very different.
Oh, you mean like this, for example, has not the right scaling? The shape is not the right. If you would use your nice functions with this radius, it would not fit on each other. It's not form invariant.
Okay.
Of course.
I think it's true that when you have narrow resonance, so closed channel dominated, then the three-body parameter is given by the R star scale. So basically, this is what is pushing. So it's not sensitive to the cutoff, but it's sensitive to
Absolutely.
the R star. So in this sense, I would say that the left side is not universal, but the right one is universal because it's sensitive to the R star parameter. Well, in the left.
I mean, this is very much semantics, one has to say here. So what one should do is, let's say, universality in the strict sense. Here's nothing universal, but if you go to the unitarity point, period, in the strict sense. Change microphysics, no change of macrophysics.
Yeah,
If you go to this more extended universality in the more broader sense, one could call it a robust universal picture. You change microphysics and it does not change much. And here it's absolutely right, as you say, it's determined by R star, the spectrum.
and R star is not microphysics, it's
Yeah, it's right. You can extract it from macro. I would careful with this, because R star is actually given by the conversion coupling G, and this is in my Hamiltonian. So if I change it, no, I would not agree that this is a macroscopic quantity.
But if you just measure the profile of the Feshbach resonance,
Yes.
you can extract R star from
That's
there.
true,
So,
but it's still part of the microscopic definition.
okay.
I find this distinction between micro and macro physics very artificial. I mean, the scattering length also depends on
Okay.
at short distances. And so in principle, and for the three-body parameter, you could just take a binding energy of some three-body state very close to threshold, and it's also a long-distance property.
Right.
Yet it-
Yes, okay, no, I agree with you. Okay, that's correct. Yeah. But it's also a bit artificial, the discussion, in some sense, very semantic.
But you can make a sharp statement, right? You can say that on the left-hand side, what is the lowest state is sensitive to the range of the interaction.
It's sensitive here to the van der Waals length, yes.
Yeah.
While here it's on R star.
It's R star,
Yeah.
which sometimes is of the same order, but might be.
You know, if you give me a second, I will come to this, then maybe. Damn it. This is not good when no one is on microphone.
Question.
Yeah, sure.
If you have the two-channel problem and you look at bound states there, you might have one which is very extended and one which is smaller radius, right? Or not?
If you include that in your model, which you don't, let's
So
assume.
you don't have a bound state which has a small size in your model?
We only have a bound state of a small size if we are far away from the Feshbach resonance at small positive A. Then it of course becomes small. But we do not have like two states, like one in the open channel, one in the closed channel.
That's my question.
No, we don't.
You never have that.
I guess that what they call two-channel model is not really what they draw with the two potentials.
Yes, absolutely. I will come to that actually in a second. When I draw this, you're all going ahead. When I draw this, what we actually have is no potential, red potential at all. We have only particles propagating on the atom threshold, going into a different channel, which is not the scattering channel, which has a bound state. There's no background potential in our case. So with respect to this, you could say it's a 1.5 channel model. We have, of course, a scattering threshold, one channel, but I don't know if one typically calls a scattering threshold without potential a channel. Well, one should, but I'm confusing you.
Yeah, I mean, I thought you had an atom channel and a molecular channel.
I don't have an explicit, I don't have an explicit term psi to the 4, which would be scattering purely in the background red, in the red background channel. I only have, which are meant here, solely, the interaction is solely given by the exchange of the closed channel molecule, nothing else.
So why didn't you include that?
One can. To be honest, we were doing that historically. The reason was we had done all this, and then on January 10th, your paper came out. So we dropped the whole calculation which we had with the background channel and just wrote up the paper. To be honest, what was the history behind the background channel?
But you can include it.
Yeah, I mean, this was a paper by Braten on the contact. Everything is in there, where they use the two-channel model. And look even at the RG. So let me go to my final results. This is connected. Maybe I skip some of those. We can look, for example, at these universal ratios, or presumably universal ratios between the scattering length where the trimers hit my atom threshold. They are completely universal at the unitarity point where you get this famous scaling to 22.7. However, of course, the lowest state don't obey the scaling law, but deviate from that. And from our solution of our model, we find then that as we go to higher and higher excited states, we approach more and more these universal numbers. Now, this is much dependent on how strong the Feshbach resonance is. You get different numbers. Now, for example, like a few weeks ago, there was this experiment by Hudson and Krim, and they found the first two Efimov resonances for broad Feshbach resonances, and they saw also a value, for example, for this ratio smaller than this 22.7, I think 21 or something. So this is in the trend of actually measuring smaller values. Now what one can do is, one can plot this now really as a continuous variable of the strength versus this quantity of these ratios, and here for the first two levels, the second two levels, and one sees that it's approaching the universal result here very quickly. Now you can also do this for the spacing between these energy levels, and you find similar curves, very quick convergence to the universal window, and you can compare also like the binding wave vector times A minus, and you find a similar picture. Now what one finds from that is, if you would have an experiment which is by accident intermediate Feshbach resonance strength, like around 1 would measure actually according to this model, one would measure exactly universal ratios, but it would be more like a coincidence, because exactly at these points we have the crossing through the results of the universal theory. So one has to be a bit cautious when one claims from the first 2 or 3 states that one has universal numbers. One can actually not, of course, not expect to measure universality away from unitarity. So now to what Sergei said, if we plot now our final result, what is A minus measured in terms of the van der Waals length versus the strength of the Feshbach resonance, one finds that for broad Feshbach resonances, open channel dominated ones, the van der Waals length sets the relevant scale. And what we find is that the value we get here for the form factor I showed before is minus 8.2 van der Waals length, and depending on the form factor actually chosen, you get a plus minus 10% deviation from that. This you can compare to the measurements of broad Feshbach resonances and the 3-body parameter, and yeah, it just shows a simple model for Feshbach resonances can explain by choosing different microscopic realizations that you will always find in this ballpark of values, and that you can also compare to a single channel model, this calculation I just mentioned, and there one finds a similar quantity. However, what is here that one focuses much more on this mechanism of Feshbach resonances, where here it's really a microscopic calculation with realistic single channel potentials. Now, however, if you go to narrow Feshbach resonances, these closed channel dominated ones, we find that R star is actually taking over as the parameter. And we find that this A minus is scaling really linearly with this R star parameter. And if we go to higher excited states, like the 4th or so, we recover this exact result predicted by Petrov already 10 years back, that A minus should scale like 12.9 times this effective range. So of course this is recovered because it's just, if you go to the unitarity point, we have to recover the exact result for this Feshbach resonance models.
A minus is defined.
So this should be A minus for a n for a highly excited state. Sorry, I should have written
The text above.
again.
In the text above the formula, it says n minus.
Oh yeah.
But
Thank you.
This should depend on the index n, right?
No, if n is very large, you get this number. Oh, okay, of course. E to the minus pi over s is 0 times n.
I see, okay. This is a perfecto.
Yeah, of course. but it's so long to write all these prefactors all the time. The most important thing, now there was this Florence experiment after we had our paper, and they did a very careful job now in potassium and measured that even for narrow resonances, it looks like the A- parameter just sticks on the line of open channel dominated resonance. So what we probably in some sense should have done, it doesn't fit our theory at all. If we would have stopped our calculation and said, let's only look at open channel dominated Feshbach resonances, well, we also would have just this line with a vendor of 10% and it would fit perfectly. However, we solved this model exactly and this we get out, we cannot do anything about it. But it shows us this model is not sufficient to explain this. So this I skip, and just to say we tested universality in this problem by choosing different form factors, and as I said, we get this 10% window. And this is very similar, in fact, what you found in your paper. Choosing different potentials, you get about 10% deviation of this A- parameter in the limit of broad Feshbach resonances. In fact, one comment, if you go to this narrow Feshbach resonance in this model, what is interesting, we find that the scaling of this A- for the highly excited states, it approaches this universal number predicted by Petrov. However, all these numbers turn out to be completely independent of the regularization scheme or the form factors. So here, this comes back to this question before. Here the full spectrum becomes completely universal. Each of these numbers is universal. This was actually also discussed in one paper by Braten, or suggested that something like this might happen. And what we find is that as we look, for example, how these ratios approach their universal number, we find that there's an exponential decay towards the universal number, and you can calculate these universal numbers. Finally, we included also a three-body force. Of course, cold atoms have three-body forces. And in third order perturbation theory, you get the famous axel-roteller potential. Well, this is honestly too complicated for our calculation. So what we did is we did a toy model, including a three-body force where we have the atom-dimer coupling constant, which is a contact interaction, to get a feeling how important three-body forces are. And what we find is that even for infinitely strong attraction...
The nature of that force?
Again?
I understand there's three dipoles you see interacting, you see, but I've never seen that type of interaction. Can you explain the nature?
So if you look at the three...
Dipole interaction, how it appears, but I didn't see three dipoles.
So I think it's really, if you look at diagrammatically, it is a diagram with a three. So it's so all permutations of the three photon exchange between three particles.
But that's not a true three-body interaction. It's iterated two-body interaction.
Well, but how do we get our von der Waals interaction? By integrating out the photons. So if you go not only integrating out the photons in the two-body problem, but in the three-body problem, on third-order perturbation theory, you would get such a potential. So it's kind of, if you do the EFT step before, or the integrating out fluctuations on the scales from...
Do you take the dipole-dipole interaction in the two-body channel too?
Oh,
Because that's pretty strong, if it's there. It's 1 over r cubed, so it's pretty strong. It's much stronger than the van der Waals.
where in the...
In the two-body channel.
There's a 1 over r cubed.
No, it's induced. It's not, you have no dipole moment in your system.
No.
This is all induced.
This r cubed is when I integrate out now the fluctuation starting from my model. Then I get an r cubed in the atom dimer.
Induced dipole.
So, so this is definitely the induced dipole-dipole interaction, and this should only, the axel-roteller term, that should only apply at long distances. So that's not actually a short-range physics. So
Which comes out, but it comes out of integrating out the photons.
Sure, but it's at long range, right?
It gives you a long range.
It comes from
This formula is only long range, absolutely.
separated atom picture.
And you get corrections here to this r to the, how does it go on? 12, yeah, and so on. Actually, James Bappe at the item calculated all these coefficients, and we discussed that a lot.
So, I mean, I think there is a question as to why you
Oh,
And
as I said, this is really just to get a flavor of what might happen using a three-body force. It's very difficult in these calculations to do that, but I wanted to have a feeling for it, how important it is. Absolutely. I have only one more slide.
okay, great.
So here we get this, and to actually summarize now the results from several papers, also from Nikolai, and the single channel calculations, actually kind of a robust picture of a approximate or robust approximate universality in the limit of prod Feshbach resonances, and you get it from two channel models, single channel models, so it's rather a robust thing. So if one combines those things, one could really speak of, yeah, we have some understanding what's going on. However, instead of a summary, as the yeah, of course, we have a problem that the model does not work for narrow resonances. And this comes back to the question, actually, what does our model do? Well, in this regime, obviously, also single channel calculations cannot be sufficient. Just, it's not the right model. But also our pure two-channel model is insufficient. And as I said before, we neglect actually the background potential. Even if the scattering length, the background scattering length is 0, it's still there. So what might happen is that you should actually do a calculation with a realistic two-channel model, including a weak open channel interaction, actually, and this is important, in the density channel. There had been many calculations using a background channel in the Cooper channel. This is not sufficient, this we checked. And then the idea is the following. If I have a narrow Feshbach resonance, I use the narrow Feshbach resonance, the exchange with this molecule, to produce a large scattering length to get this large 1/r² tail and get my highly excited Efimov state. Now what might happen, what happens if I don't have my background scattering potential, the R star parameter will cut off my potential at this scale and make it very repulsive. This makes my lowest trimer state very weakly bound, which corresponds to going to very, very large scattering length here. However, if I would have a background potential, this potential itself might have a small scattering length, but it might be very deep and then very quickly rise to values. If I combine both, it might happen that the interplay between both, the narrow resonance is responsible for giving you the large scattering length, while the open channel contribution is needed to actually get the suppression at about 2 times the van der Waals length of the probability to be there in the scattering process. So if you combine those, I would actually guess that these things can be explained. Of course, our model is not sufficient in this limit, but that might be enough. So one could work on the minimal model in this respect. Yeah, and with this, thank you.
So I think we have time for maybe one more question, and then the rest of the question we have in the afternoon.
Maybe I have one question. If you go back to your predicted dependence, this plot, is there a chance to have an experiment with some atoms on the left side?
You mean here?
Yeah.
The problem is that the magnetic field control has to be extreme in these experiments. So these resonances will be very tiny in magnetic field range. And then to get your coils so perfectly without eddy currents, without anything, to tune the magnetic field on the range here, we would talk about micro Gauss. There is a different possibility.
It depends on the absolute value of the magnetic field as well.
Yes. So, but then you would deal with the quadratic Zeeman effect at low magnetic fields, for example. You don't want to do that because then you can also induce against spin-changing collisions. This would be not clever, I think. Especially in potassium, you have F equal 9/2, so you have 10 spin states. You are only protected by the large magnetic field. So this would not help, I think. Yes. Did I? No, there's one more thing. You can use optical Feshbach resonances. There you can actually tune this R star parameter. There are proposals, maybe this helps. But then one has to think about, is a two-channel model with an exchange in this way sensible?
The magnetic field control now, as compared to 10 years ago, is a lot better. So from that point of view,
Sure,
it's not-
sure.
I mean,
I would also say if this is a grant meeting, one would probably say, of course we will do that.
It was this visionary comment and close the morning talk.
Yes.
Speaker again.